Hello there. saying thank you for throwing his soggy ball again and again. Yes, Buddy, and again. But mostly, he wants to say thank you for his happy place. Oh, and for picking up his, you know.
Dogs Trust know that if dogs could talk, they'd say thank you, just like Buddy. Help us give every dog a happy place. Dogs Trust. A dog is for life.
Mr. Q! Winning! Losing. At Mr. Q Casino, that's just part of the game. Want to always win? Play a vending machine. You win, you love Q. You lose, you hate Q. Mr. Q, the casino you love to hate. And you'll love 100 free spins on Big Bass Splash with your first deposit. Play at mrq.com or on the app. UK 18 plus residents only. Minimum £10 first deposit, 10p per spin. Free spins must be used within 48 hours of depositing. All winnings paid in cash. T's and C's apply. Play safely.
Let me go, there's no doubt. Gotta get out of this small town. You took my heart from me. Now you're everywhere I see. Set me free, let me fly. Let me find new kinds of highs. We're just wasting here, waiting for another year. We both know the score. We've been here once before. So many words unspoken. You took my heart, it's already broken. You don't have to wait. I can take the pain. I will surrender. Let me go on a new adventure. On a new adventure. On a new adventure.
Good evening and welcome everybody. This is Obi-Wan Pez 4 and Simplex Pachinko. We're a little bit off. It's fine. Gonna be doing some math tonight. And I wanted to make sure I had a command working before I got on. So let's see if this works. Awesome. Cool. Okay, so we got okay, that needs to be, it's almost correct. Needs to be ever so slightly changed so that we can put a space in there and in there. Cool. Okay. So now we've got it so that should be a space after the exclamation point, so it won't look all weird. Okay, and let's just check something real quick. Okay, well, that does work. I just double checked, and Euclidia, the game we were talking about last time, that is, oh, that's unfortunate. Got another hole in the glove. The math game we were talking about last time that is available on PC and is usually used on like iPhone or whatever, is going to be available. So we're able to use it as a category here on Twitch. So that's kind of nice. Okay. for now, let's figure out what we want to do. So, it being a Friday, this is usually a game night, but I haven't done math since I was back, so it seemed like it was probably a good idea to, you know, at least do one math stream this week. Astro Canucks 3D glasses got my stylus trapped. Okay, so right, here's a good basic one. So if we wanted to prove the irrationality of the square root of 2. Okay, so rational numbers may be expressed as a over b, where a and b are both integers, and b is not 0. So in order to prove the irrationality, what we're going to do is that we're going to prove that the assumption that root 2 belongs to the rational numbers is impossible.
We know what you're thinking.
Or leads to contradiction.
You want more Alan Carr? Well, good news. Changing Ends is back on ITVX. Oh. It's not just you. The critics can't get enough. The Guardian is raving, calling it camp, cheeky and clever. And the Independent says he's the making of a national treasure. Sounds like they
Okay, so
much as you do.
really the first thing that we need to establish, and like this is never actually talked about in any context whatsoever.
Why?
Right, assuming that the square root of 2 is at least a real number. We do know that for some subset, let's call it, let's not use A or B. For some subset S belonging to the real numbers, all R belonging to the real numbers will either well, will satisfy one, R belongs to that S, which is a, S is a subset, could be proper, could be improper, of R, right? So all R real numbers within the real set will either belong to S, right, or exclusively R belongs to the reals excluding S, not singleton. So something that we just need to establish first. For any subset of the real numbers, all real numbers either belong to that subset or belong to the real numbers and not that subset. In other words, the complement, right? So it is in S, exclusive, or it is in complement of S, also known as S bar most of the time. Right, which does still need to be a subset of the real numbers itself. Okay. So with that assumption established, we can know, or this directly leads to the assumption that either root 2 is in the rational set, which is a subset of the real numbers, and in fact we know it's an improper subset. There are things that exist in the reals that are not rational. Right? Exclusive or root 2 belongs to the reals without the rationals. Making no assumptions about what it's actually called, but nonetheless, we're just saying those are irrational. Right, so these are rational reals, and these are irrational reals. Just a note on the side. The real numbers are partitioned. Into rational and irrational numbers. right? And partitioning means that either something does belong to it or something does not belong to it. It is a simple binary, either it's yes or it's no. It is possible that there are multiple partitions. So for instance, sectors on your hard drive can belong to any one of a number of drives, but they cannot be claimed by more than one drive. So you're not able to have a particular area, a particular sector on your hard disk that will have things that are in drive F and drive G. It's not possible. Okay. So with that, right, as long as we have established that either square root of 2 is rational or it is irrational and it is real, there's no other way for this to work. So, we will assume root 2 is in fact a rational number within the within the subset of rational numbers of the real numbers. So square root of 2 may be expressed
The best things in life are all heroes, no zeros. Take Santa and his reindeer. Sure.
as
The headlines.
a ratio
Could he do it without Dasher, Dancer, Parities,
of
Comic
2 integers.
Never. You need every single one of them. Together.
And we'll say the square root of 2 is going to be equal to a over b.
Heroes. It wouldn't be Christmas without them. The best groups are all heroes, no zeros. Like Cadbury heroes.
Right, such that b is not 0. Right, we already know that a and b are both integers. I guess we can also rewrite that if we felt like it. Okay, so therefore, we say that 2 is going to be equal to a over b, will represent a fraction in lowest form. That the greatest common factor of a and b is going to be 1. You can also say that they are mutually prime. What are some other words for that? Share no common factors, etc. Right, you can call it something like that. So if we were to take the square root of 2 and multiply both sides by b, we would get that the square root of 2 times b is equal to a. And then if we square both sides, we end up with a 2b squared is equal to a squared. And it is worthy to note here note that since b is an integer, b squared is also under the integers. By closure of multiplication. So no matter what integer you start with, if you multiply it by any other integer, you will always get another integer as your product. In this case, it's b times b itself. So an integer times itself is also going to be an integer. We don't have to prove that. If you are taking abstract algebra, you may actually have to prove that, so just keep that in mind. And since b squared is an integer, a squared equals 2b squared implies that a squared is even. Right, so we have an integer, we multiply it by itself, and we end up with excuse me. Right, we have an integer, we multiply it by itself, and then if we multiply by 2, that's telling us that twice any integer is going to be an even number. So a squared must be even according to this logic. And then we have to do a short little lemma on the side. If a squared is even, then a is also even. Now it has already been established that a is an integer. So in this case, we know that a squared is also going to be an integer. It's going to be the it's going to be within the set of even perfect squares. Or a squared is going to be in the set of even perfect squares. So then, if we have that, then we should know that a itself, the number we started with, is also even. Now, in order to do this, we have to do it in a slightly roundabout way. Let's just challenge everybody. Can you think of any a squared that is even that then you come back and be like, well, the a that got us there in the first place, turns out it's odd. Somehow I don't think you can do it. So what we do instead at this point is we say, okay, we're going to do a little short proof over on the side, call it a lemma. we're not able to show by direct proof that any a squared that we get is going to be even, therefore a must also be even. Instead, what we're going to do is we're going to use the contrapositive. All right, for the implication, A implies B, its contrapositive is going to be not B implies not A. So in this case, we're going to say the opposite statement, or the negation of each of the individual statements, and we're going to flip the order of the if and then. So therefore, the contrapositive of the above statement is if A is not even, then A squared is not even. Right, and that's the other thing. You can't show up a direct proof and can't find a counterexample. That's really important, right? Try to find a counterexample to the statement that you're trying to prove in the first place. If it's easy to find a counterexample, state it. But any a squared that we can think of turns out, right? 4, 16, 64, 36, right? All of those look like they're all divisible by 4. Right, and in fact, we could even do a little one on the side. Right, so our proof is going to be for this other one, right? If A is even, that means that A could be expressed as 2n, where n is an integer. So A squared is equal to parentheses 2n squared, which is going to be equal to 2n times 2n is 4n squared. Since n belongs to the integers, n squared belongs to the integers, again by multiplicative closure. So here, a squared equals 4 times n squared implies that all a squared are multiples of 4. So all a squared are divisible by 4. Well, works out alright, I think. So here, right, we've already shown over there that if a is an even number, then a squared will be divisible by 4. So going the other way, if a squared is even, we already know that all a squared that are even, well, no, that's not true, right? Yes. Okay, we've effectively shown, going the other way, that if we started with an a squared and it's even, it must have come from an a that is also even, just because of the options of partition, right? A squared is even, a is odd is not actually possible. We've already seen that. Right, so a squared is, if a squared is odd, then we haven't really shown what that could possibly come from, but we're about to do that here. And no surprise, right? It's always going to end up being evens yield evens, odd yields odds, and then we just have to sort of prove it, because otherwise somebody could say, well, you know, it is theoretically possible for us to think about this other thing.
Dogs trust know that if dogs could talk, they'd say thank you, just like help us give every dog.
Right, if a is not even, then a squared is not even, is going to tell us, okay, so if a is odd, then a squared is odd. And this is an equivalent statement to the above, because integers are partitioned into even and odd numbers. So if it is not an even number, it must be an odd number. We have established that our A and our B in all these cases are going to start as integers. Okay, so if A is odd, then A squared is odd. So A cannot be expressed as twice some integer to n. So A mod 2 cannot be equivalent to 0. A mod 2 must be equivalent to 1. So A must be of the form 2n plus 1. You could do minus 1 instead, you could do whatever you feel like, but this is the idea. Anytime that we divide this particular number by 2, we should end up with a remainder of 1. Right, mods are looking at remainder. So here, a is equal to 2n plus 1. When we try to divide by 2, we divide 2n by 2, we get n left over. And then we try to divide the 1 by 2, we can't do it, and it is the 1 remaining. Right. So a is of the form 2n plus 1. So what happens when we say, give me a squared? This is 2n plus 1, parentheses squared, which is 4n squared plus 4n plus 1. All this stuff is also belonging to the integers under multiplicative and additive closure. So therefore a squared is going to be equal to let's take a 2 out and leave it with a 2n squared plus 2n. This is 2 times an integer. Let's call it k. Plus 1 was left over. All right, there we go. Right, so do that up here. Let 2n squared plus 2n be equal to k belonging to the integers. So therefore, a squared mod 2 is going to be equivalent to 1 as well, or is going to be not equivalent to 0. So a squared is not even. Is odd. Say whichever, right? And that's going to get you your quoterat demonstrandum. Now I did, right? This is a little ridiculous. We did go into like super detailed stuff here. Enochian, good evening and welcome. What's a good course or website to learn math? What level? I'm a little biased, but like this one right here. But yes, on demand, of course. If you're going for anything from basic math all the way through differential equations, and really all you need is like a tutor. Ninth grade years ago and never got into uni. Okay. So if you want something into, again, basic math through to differential equations, and you just need like a tutor, Khan Academy, I find, has been pretty good for students who, again, just need a tutor. If you need somebody who like goes through and specifically goes through all of the reasons why things work and how they're interconnected to all those other things that are out there, Salcon tends to fall a little bit short, but he's also not like a math teacher. He was a tutor, so it makes sense. If you do like Paul's online notes, or that's text only though. Right, so that is for Paul's online math notes. I like it as a text resource to go through and say, like, you know, what are the step-by-step reasons why we do all these things? Not just to say, here's how to get the answer. Again, that's more of a tutorial style, whereas Paul's is like, this is an actual teacher who goes through and teaches you all these things. Again, shows you all of the ridiculous, sometimes tedious perhaps, connections between the individual things. But that's kind of my style as well. I like showing off all the cool stuff. Okay. So, we've just now shown that if a squared is even, then a is also even. So this is going to take all of this stuff, which we typed up like 10 minutes ago, and this lemma, bring it together, and now we're going to be able to say that since b squared is an integer and a squared is, oops, is even, we know that a is even. Okay, so we had this up here. Since b squared is an integer, we know that a squared was going to be equal to 2b squared. B squared is an integer. This is twice an integer, so therefore a squared is even. The lemma shows us that if a squared is even, then a is also even, which then allows us to say that b squared is going to be equal to 2a squared. And since we know A is even, we will be able to say that b squared is equal to 2 times twice k, where k is an integer. Right, so twice some other integer. Well, hang on a sec. Now that means that b squared is going to be 4 times k. Oh, I didn't... Hang on. Okay, yes. Since a is even, let a equal 2k, where k is an integer. Alright, let's back that up a second there. Yeesh. So 2 times, parentheses 2k squared. That's going to be equal to 2 times, we already know this from before, that's 4 times k squared. So that means that b squared is equal to 8k squared. Or, actually, we can back that off a little bit. 2 times 4k squared. Since 4k squared is an integer by closure. Oops, not there. There. Since 4k squared is an integer, then b squared equals 2, again, m, where m is an integer. Implies b squared is even. And guess what that means? Since b squared is even by our lemma above, b is even. Lemma green. So, this means that a over b is the ratio of 2 even numbers. You use Xernal++. Yeah, I'm using Excalidraw, which is an online thing. It works pretty nicely. If you need to share the space with multiple people, it gets a little clogged. It tends to run out of memory space, allegedly, fairly quickly, but I think that that's mostly because it's trying to, like, use this whole thing as one instance. It does some weird stuff. I'm not sure exactly. I might be sending it out to everybody individually and taking up extra RAM. I don't quite understand exactly, or whatever. Taking up more bandwidth. So A over B is the ratio of 2 even numbers, but that the GCF, greatest common factor, yeah, of A and B should be equal to 1. So here we have a contradiction. So the square root of 2 cannot be expressed as a over b, such that a and b are members of the integers, with the exception that b cannot be 0. Or, with the exception that b equals 0 is removed, I guess. Right, so this is telling us that can't be rational, so it must be irrational. That's the only other possibility, right? The square root of 2 cannot be a member of the rationals. Square root of 2 must be a not subset, member. It must be part of the reals without the rationals. Right? So this is, again, a little bit overkill. We did a lot of extra steps in proving that the square root of 2 cannot be rational. So first of all, if we must establish all of the facts of everything, then we would need to go back and say, okay, so a rational number may be expressed as a over b, where a and b are integers and b is not 0. So therefore, we need to prove the assumption that the square root of 2 belongs to the rational numbers is impossible or leads to a contradiction. Assuming that the square root of 2 is a member of the reals, we know that the reals can be partitioned into either numbers belonging to a set or the numbers belonging to the rest of the real numbers which are not in that set. It is partitioned. And in this case, we said that the rationals and irrationals form this partition for the relevant facts that we want to talk about today. So we went through and we said that, okay, assume that the square root of 2 is a member of the rationals, which is a subset of the reals. So it may be expressed as a over b, where a and b are integers and b is not 0. A over b should represent a fraction in lowest form, i.e. GCF of a and b should be 1. They're mutually primed to each other. And then if we do some simple algebra here, we just move the b over to the other side. We get square root of 2 times b equals a. Square both sides, and we get 2b squared equals a squared. Since b squared is a member of the integers itself by closure, then 2b squared is indicating that twice an integer makes an even number. So a squared must be an even number by virtue of b squared being an integer, and twice an integer is even. Then we did a little bit of a lemma over here, which said that if you start with the assumption that a squared is even, we can prove that a is an even number as well. So once we did that, and that goes all the way down here, we came over here and we said, okay, so b squared is an integer and also a squared is even, so therefore a must also be even. by the lemma we just showed. B squared is 2a squared. So a squared, again, wow, okay. Where did that come from? Give me a sec. 2b squared equals a squared. Yeah, I think I just messed that up. Cool. Good times, good times, good times. Yeah, I think I went backwards on this, so we're going to have to fix this. Go the other way. Oh, man. Alright, so this is 8. A squared equals 2b squared through all this stuff. And again, I knew something was wrong. I just couldn't quite put my finger on it. Okay, we'll hold off on that. And then here, we'll get rid of these parentheses because we don't need them. Here, we do know that we could divide both sides by 2. So b squared equals 2k squared, and that's where it is. Not an 8, not a 2 times 4 times something. No, no, no. That goes over there. So if b squared equals 2k squared, and k squared is an integer by closure, therefore b squared could be 2 times m, some integer, which implies that b squared is even. And by the lemma that we just showed, since b squared is even, b must also be even. So a over b is the ratio of 2 even numbers. Okay, there was just that little tiny bit in the middle that we had to correct. So, good times. Okay. Let's go. Ad break's going to start here, so let's. Okay, so first of all, let's sync up my date and time over there, because goodness, I don't know what's going on. I would like you to synchronize it now. There we go. Anyway, let's go and take the ad break, and then we'll be back in 3 minutes, and we'll do another kind of common problem that comes up a lot. So, see y'all in just a few. Thank you so much for coming. Right. So we're going to get back into lifting some weights here. Hope everybody's having a good Friday. Here in the UK, we just had Boxing Day, which was for us a matter of just sitting around the house and eating leftovers. We did actually not sit around the house all day. We went to a local castle, which is really just a giant manor house. It's not like, old-timey castle. It's new-timey castle. That's just a bunch of, a rich family that owned a bunch of land, put a large manor house on it. So, I don't know how long, I forget how long it's been around. Since like the 1780s, certainly. So they do up their castle every year to have some sort of theme decoration. Let's see, the last couple of years were Alice in Wonderland, and I think there was one before that we had heard about, like our friends from our friends who had been living here before told us what the previous year's one was. I forget what that was. This year they're doing Wizard of Oz, so that's kind of fun. It's off near York, so if anybody is interested and is going to be in the York area, can go check it out. It's kind of neat. Looks like my not so D&D group is going to be meeting tomorrow. I'm currently GMing a game of Titan's Grave, the Ashes of Volcana, which was a Geek and Sundry TTRPG that was put on by Will Wheaton, and Felicia Day had been CEO of Geek and Sundry at that point, I think. So she got Will to run a TTRPG in Fantasy Age with his son Ryan as as a lead author, maybe, for this particular campaign. It was really cool. I was kind of sad that it only went one season, but, you know, things happen. So I have written a beginning and tried to keep like a theme, sort of, going through it. So if any of my players are watching, haha, very much doubt that they're watching this channel, but nonetheless, if any of my players are watching, there is actually like a theme going, sort of. Maybe you should talk with more NPCs. All right. You know what? Truth tables. We should probably do a couple of truth tables just to show. Oops, nope. I think we need 4. So I think all we're doing. Yeah, okay. This is how we do it. Okay, so we got A, we got B. we've got A implies B. Okay, and then we've got not B. Not A. And not B implies not A. All right, so we need every possible combination of A and B. So we've got, and what combinations they could have in a logical statement. So we could have that A is true and B is true. We could have that A is true and B is false. We could have that A is false and B is true, and we could have that A is false and B is also false. Okay. So in a logical implication, A implies B. If the thing that we are saying, if A then B, if both of the pieces are true, then the implication itself is true. I think that's pretty easy to see. So for instance, right, if we say, if it snows tomorrow, then we have school. That might be a little tricky. If it's sunny tomorrow, then we have school. Right, so let's say that it is sunny tomorrow, and we do have school, then that implication, if it is sunny tomorrow, then we'll have school, is also true. Whether it is a sound argument is more of a philosophical judgment. And we can also discuss like how it works in terms of, you know, whether that the statement itself is actually useful, or if it just happened to work out. We can also discuss that in terms of mathematics. So for instance, right, in a case where this is not a useful implication, if it is sunny tomorrow, then we have school, would be, for instance, today. Today is Friday. Tomorrow is Saturday. If it is sunny tomorrow, then we will have school. Well, if it turns out that it is sunny tomorrow, and we don't have school because it was Saturday, not because it was sunny, then it turns out that this is not a useful statement. And also, the statement itself is false. If it is sunny tomorrow, then we have school. Well, it's false because we just don't have school tomorrow anyway. In the case of, if it's sunny tomorrow, then we'll have school. In this case, false true, what happens is it turns out that it is not sunny. So, for instance, it is cloudy tomorrow, and we have school, being B is true. Our statement, if it is sunny tomorrow, then we have school, we couldn't test that hypothesis. So because we can't test the hypothesis, this is going to tell us that this is still a useful statement. The if-then statement could still work. We just don't know because we didn't have the chance to test it. Which also means in the last case, false, false, this is also true, which makes a lot of people very angry. Right? But the point is that we didn't have a chance to test this hypothesis. So this hypothesis is still valid. This hypothesis is still true from a certain point of view. Okay, so going the other way, now we have not B. So if we look at the truth table back in the second column, all we're doing for not B is reversing all of these things. So it's going to be false, true, false, true. And then same for not A. We're going to take these four and we're just going to reverse them, negate them. So false, false, true, true. And then we're going to take the exact same ideas that we had for A implies B and apply those same combinations to not B implies not A. So in the first case, right, not B implies not A is false, false. Which means, again, the hypothesis, not B, is not being tested. So because the hypothesis is not being tested, we could still use not B implies not A to potentially predict what's going to happen in the future. Not like, future prediction, but it might be a useful statement. It might be a useful if-then cause and effect. So in this case, right, okay, so if it is sunny tomorrow, then we will go to school. Now has the contrapositive. If we will not go to school. Then it is not sunny. Let's imply the tomorrow here. All right, English is weird. No, that's not A and B. This is not B and not A. Okay, so again, here with not B and not A being true, then false, this gives us the exact same problem that we had before. It is not helpful. This statement was disproven. If we will not go to school tomorrow, then it is not sunny. Again, what if it was Saturday tomorrow? We're not going to school because it's Saturday. Again, it has nothing to do with the weather. So this would not be a useful statement. So we say here, that's going to be false. Again, if we will not go to school tomorrow, then it is not sunny, and we do go to school tomorrow, then again, this new hypothesis was never tested, so it's still a potentially useful statement to use. We're not going to declare it to be false. This is still potentially true. And then likewise, if we will not go to school tomorrow, then it is not sunny. If both parts are true, then this implication is true. Again, you could argue that maybe there's a different reason and this is just a coincidence, but the logical statement, the implication that we're using is still going to be potentially useful. So we say that the implication at least appears to be true based on what happened in the world. And now notice, right? A implies B and not B implies not A have the exact same truth values in the exact same locations going across the table. So when A was true and B was true, we had both A implies B and not B implies not A as true. When A was true, B was false, both of those statements were false. When A was false and B was true, then we had a true statement overall in both cases. And again, when A was false and B was false, then we had a true implication in both cases again. So, makes for an interesting sorting, I guess, to go through and make sure that all of your potential truth values are showing the same sorts of things. Right? If they show exactly the same thing in exactly the same places, those things are logically equivalent statements. All right. Okay. Complex partial fraction decomposition. So I've never actually done this before, never seen it either, but let's check this out. So this is saying find find real constants A, B, and C and D, E complex constants such that
Mom, can I use the tablet?
Are we there yet?
Can someone check we're going the right way on maps, please?
Are we there yet?
A over X
Here you go.
plus
Can someone call Nan to let her know we're on our way?
BX plus C over
Besting this Christmas?
X,
You need the UK's best
X squared plus 1, which is identical to A over X plus D over X plus I plus E over X minus I.
Is where you'll find your next great story, whether it's Fantastic Four, First Steps. We will protect you. High-powered drama, All's Fair.
Tell us your story.
Or brand new
So is this going to work, is the idea. If we introduce complex constants, D and E,
subscription required.
okay, So this is going to be 10x squared minus 2x plus 4 is equal to multiply all the way across by x cubed plus x. So a times x cubed plus x. And in fact, we can just back this off a little bit and say, okay, we know that this is going to be ax times x squared plus 1 all over x plus d times x squared plus 1 over x plus I plus e times x squared plus 1 over x minus I. Okay. So 10x squared minus 2x plus 4 is equal to. Here we get that the x's are going to divide out. Here we get that our x plus I will divide out from x squared plus 1, and we're left with x minus I. And then similarly on the end, x squared plus 1 is divided by x minus I, and we're left with x plus I. So here we get a x squared plus a plus dx squared minus di x plus ex squared plus ei x. So this is saying that a plus d plus e times x squared plus negative d plus e I x plus a is 10x squared minus 2x plus 4. Okay, so it seems like a equals 4 has to be an answer. And then we get d plus e is going to be equal to, 4 plus d plus e is going to be equal to 10. And negative d plus e parentheses times I is going to be equal to negative 2. So d plus e is going to be equal to 6. So here, if we make this negative 2d plus d plus e, all parentheses times I is equal to negative 2, this is going to tell us that negative 2d plus 6 times I is going to be equal to negative 2. Now, for my money, this is a little bit alarming, but can make this work. So negative 2i times d plus 6i is equal to negative 2. Bring it to the other side is negative 2i times d is equal to negative 2 minus 6i. If we divide everything by negative 2, then we get I times d is equal to 1 plus 3i. Should have left it maybe. Right, so if we multiply everything by I, then we end up with positive 1d is equal to, multiply the other side by I as well, we get negative I plus 3. 3 minus I. Which means 3 minus I plus E is going to be equal to 6, which means E is going to be equal to, subtract 3 from both sides, we get 3, add I to both sides, we get plus I. So E is here, it is the complex conjugate of D, which is not surprising. And then we also get that A is 4 up there, so therefore that thing. Right. Is equal to 4 over x plus d 3 minus I over x plus I. Yep. Plus 3 plus I over x minus I. So if you were doing complex partial fraction decomposition, seems pretty good on that one. Cool. So yeah, then we it does say find B and C as well, so suppose we could go back to the beginning to do that one. Just to compare how much work it would take, I suppose. Equals A over X plus BX plus C over X squared plus 1. Okay, so if we multiply all this through by same stuff as we did before, get 10x squared minus 2x plus 4 is equal to A times x squared plus 1 over x plus bx plus c times x squared plus 1 all over x squared plus 1. Those are gone here. Those are gone there. So 10x squared minus 2x plus 4 is equal to ax squared plus a. Same as before. No change there. Here, this is going to be a bx squared plus cx. This is a plus b x squared plus cx plus a. So here again, a equals 4, b equals 6, and c equals negative 2. It took literally no time here. So so it is helpful, I suppose, if you need to break it into linear factors and you want complex constants attached rather than having x's. I guess it could matter. I suppose if you're doing integration, it would not particularly be helpful to have a some kind of polynomial in the denominator, and then a not particularly nice polynomial in the numerator. In this case, though, like if we were trying to integrate this, alright, 10x squared minus 2x plus 4 dx over x cubed plus x. Like, I would probably go with a u substitution. Let u be equal to x cubed plus x. So du is going to be equal to 3x squared plus plus 1. Yeah. So this is going to start looking pretty nasty pretty quickly. So here we'd have, well, like, yeah, well, dx. Yeah. Okay. So these constants don't have the same ratio as these constants. And then the worst part is we've got stuff in the middle. So it's not going to be particularly nice. So partial fraction decomposition might be the best way to go. We're going to get 4 over x plus 6x minus 2 over x squared plus 1 dx. This is a lot more manageable. Not just because the numbers are smaller, all that good stuff, but, right, we've got 4 over x dx is just a natural log. That's super easy, sorry. Then we've got plus here, let u equal x squared plus 1, so du is going to equal 2x dx. So we separate this out into the integral of 3 times the integral of 2x dx over x squared plus 1 plus the other part, right? Integral negative 2 dx over x squared plus 1. Right, so this 3 and this 2 multiplied to that 6 up top, and that takes care of the entire yeah, that takes care of the denominator's derivative, because that 1 is just going to go away. So 2x dx is going to be the derivative of the bottom, and we've got plenty of that up top. So this is 3 times the integral of du over u plus the integral of, 4 times the integral of dx over x. So, I mean, literally, it's the same stuff. It's just that one of them's x and one of them's u. You need to keep track of it because they all need the same variable at the end. Then we take this as negative 2 integral of dx over x squared plus 1. This is a different special integral. This is an arctangent. So arctangent of x, if we take the derivative, is going to be 1 over, or dx over, x squared plus 1. So if we take the integral here, this is going to be 4 times the natural log of x plus 3 times the natural log of absolute value of u. I guess we need the absolute value of x over there as well. Minus 2 times the arctan of x, and then we get a plus c for all of the different integrals coming together under one constant vertical shift, whatever it is. Right, so each of the individual ones could have a vertical shift, but at the end, it's the sum of all of them that's going to end up making a difference. So here, 4 times the natural log of x, absolute value of x, plus 3 times the natural log of the absolute value of u, which is x squared plus 1, which is always positive. So we don't even need the absolute value. It could just be parentheses. Always positive. And in fact, just strictly greater than 0 in the first place. Okay. And then minus 2 arctan of x all plus c. Right. So this is probably the quickest way to end up doing it. Trying to just do u substitution and like separating the fraction to multiple parts didn't work at all. What did work is decomposing the denominator from a product into the sum of some sort of constant divided by each of those things. Again, in theory, we could do this for like complex analysis and make the denominator either x plus I or x minus I, which then we're going to have to use complex analysis and say, like, you know, where are the poles for this thing? It's plus and minus I. And how are we going to do line integrals for all this? If Penn was here, he'd tell me. Yeah. That's as good as it gets. We could, in theory, bring this stuff together into one natural log. But, I mean, that's disaster. Okay, fine. We'll do it. This actually does make it a little bit easier, because this is going to be natural log of x to the 4th, which is always positive, so we don't need the absolute values, plus natural log of x squared plus 2 parentheses cubed minus twice the arctan of x plus c. And again, those natural logs can combine into x to the 4th x squared plus 1 cubed, and then minus 2 arctangent of x plus c. Alright, if you want to go a bit further, sure, you can do that. And then we could do arctan of e. No. E to the natural log of arctan. Yeah, that'd be great. Just to bring them together. That doesn't even work. You'd have to have natural log of e to the 2 arctan. I mean, it'd be gross. Don't do that. How's everybody's Friday? Anyway. We're looking at enrich, which is looking to yeah, Flofi. Yeah. I was definitely going there, but meh. Let's see. Ford circles. Hmm. Oh man. This might be a little bit beyond what we're willing to do tonight. Yes, I know. How dare you? GeoGebra applet shows the construction of a sequence of Ford circles. Ford circles have center p over q, comma 1 over 2q squared. Yeah, there we go.
Mr. Q Casino, that's just part of the game. Want to always win? You win, you love Q. You lose, you hate Q. Mr. Q, the casino you love to hate. And you'll love 100 free spins on Big Bass
P over q, comma 1 over 2q squared. And radii 1 over 2q squared. Okay, well obviously yes, the y value is just the radius because it's tangent to the x-axis. Where p over q is a lowest term fraction. In the interactivity given, you can move all sliders to choose A, B, C, and D in the next one. Centers will be at A over C, comma 1 over 2c squared. And B over D, comma 1 over 2d squared. Radii will be at 1 over 2c squared and 1 over to d squared. When they touch, they're colored in blue. Explore the interactivity, find some values of ah. Ah. Right. Explore AD minus BC for all sets of A, B, C, D such that the circles are still colored solid blue. And is there a pattern? Okay. Thanks everybody for coming. We will be right back in 3 minutes. And gonna take an ad break here. Get up, stretch, do all that good stuff. See you in just a little bit.
means you. Yes, you. We know you're pointing at yourself. When it comes to Paddy Power Games, we've got a place made for all sorts. From the experts to the drama queens.
It's me, the GC.
The finance bros. Look at those stocks, lads. We'll stick with slots. It's what we're good at. And not forgetting you. Yes, you, the one listening. Because at Paddy Power Games, we've got all sorts of games for all sorts of treacles. Eligibility rules and terms and conditions apply. Please gamble responsibly. 18 plus, gambleaware.org.
The Big Tasty is back at McDonald's, but now it's a double. It's the beefiest Big Tasty of all time ever. Oh, got a bit intense there. The new Double Big Tasty, now at McDonald's. Available until the 4th of Jan 2026 from 11 a.m. Price and participation may vary, subject to availability.
Hey Spotifyers, click or tap the banner to listen to UK Christmas number ones. Get into the festive spirit with these Christmas chart toppers. Brought to you by our friends at Pepsi Max. Your usual tunes can wait. It's Christmas after all. Pepsi Max, thirsty for more.
Welcome back, everybody. Tonight is hashtag not sponsored by some Hendrix and Fever Tree. So, let's see if we can come up with some useful values. Not vowels. That's different. I was a genius, and I took my tea cup, and I just like, I grabbed the top, and I started rinsing out under the sink, and I realized that I was still wearing my glove. Not like it's a big deal, it's just nylon or whatever. Maybe spandex. I don't know, whatever. It's all good. It's just partially dry. Okay, so let's try to find some combinations of values that will actually have that we will get blue circles, right? So that is the goal. That's not gonna work. All right, so 0, 1, 1, 1. Okay. 0, 1, 1, 2. 1, 1, 3. 1, 1, 4, 1, 5, 6, 7, 8, 9, 10, 11, 12. 0, 1, 1, n. N equals anywhere from 1 up to 12. And I believe that it's going to work indefinitely because that n there is just like showing us how much space it's giving before we start the next number, or before we like start the next circle. So they're just always going to be connected. Okay. Now if we go to like b equals 2, that's going to start shifting us out further and further. Okay. Yeah. All right, here's one that's not that. So, 4. What? Oh, I see. That's fine. 4, 1, 7, 2. And 4, 1, 9, 2. And those are symmetric to each other. See, right, those can go all the way to 12. Three, 1, 7, 2. This one also a 9. No. 3, 1, 5, 2. AD minus BC. -1. Also -1. 8. -7 is either 1 or -1. Okay. 6 minus 5 or 6 minus 7. Yeah, 1 and -1, same deal. Okay. So let's do 3 times 4, and we want to get off by 1 would put it at 11 or 13, so that's probably not going to work very well. 15. We could potentially put this at, again, 14 or 16, so let's put it there. Yep. The absolute value of AD minus BC should be equal to 1 in order to get these to actually work correctly. So now we look at this in terms of that, right? So 3, 4, 4, 5 is going to be AD is 15 and BC is 16. So if we change that so that BC is now 14, so 2 and 7. Or 8. Oh, because that's also 16. Yeah. Yeah. Of course. They are also blue. So 3, 2, 7, 5. And 3, 5, 4, 4. And 3, 5. You could do 7, 2 the other way, but this app doesn't support it. So we won't be doing that. 8, 2, right? Right, that means and extremes theorem here, right? Essentially, is what we're working out. So our A times our D minus our B times our C, what are we getting? So in both of those cases, we end up getting a -1 because we've got 15 minus 16. And in the previous case, 3, 2, 7, 5, we have 3 times 5 is 15 minus 7 times 2 is 14 is +1. So all of those cases have worked. Okay. So, interesting pattern. Why does it work, right? Can you prove? Yeah, I didn't read far enough in the thing. Can you prove that any touching circles will have absolute value AD minus BC equal to 1? Yep. So that is what we found. Cool. Why should AD times BC be equal to or have a magnitude of 1? Why is that the case? These are where the centers are, and those are their radii. Are their diameters making a nice collinear thing? So let's try 4, 1, 7, 2. I can't see that, it's too small. 3, 1, 5, 2, slightly bigger. Okay, why is that the case? Right? So what's going on with these things? No. Okay, do that. Do that. So what's the thing with both of these? Okay, the tangent point is going to be collinear with their radii. That should be easy enough to show, maybe. They're also going to have a tangent line. That they are both perpendicular to, or both radii are perpendicular to at that point. Is there anything special about this, right? I might be onto something here. I believe this makes a similar triangle. Right, these are right angles. I can't prove that this is a right angle yet. However, it should be easy enough. I'm pretty sure it's correct. I just have to prove it. Okay, so we have angles in a right triangle. Okay. That and that have to be complementary. And that have to be complementary, but they don't necessarily have to be the same as each other. Could just be a different pair. What we do have to show is that one of those angles is going to be equal to the other. How do we do that? Next question, right? Can we drop an altitude to this point, which is the tangent point to the ground, which is going to be at a right angle to the other thing. And drop a tangent point on this side, or drop a altitude on this side, and get this being a right angle. Can we show that these are the same? I think we can. Ooh. Okay, good. Okay. So I'm pretty sure we could show that these are kites, right? So we have a radius in both of those. Yeah, use big R for these two because it's in the bigger circle. We have in the smaller circle small r's. Those are equal to each other. And they share the inner portion here. Okay, so we've got an angle side-side situation going on. Don't do that. Right, the right angles, and then we have two opposite and adjacent sides. It's not helping right now. I'm pretty sure that we can show that this side and that side are the same. However, I don't remember how to do that. So there's probably a nice little axiom that says that not axiom. This is probably a nice little construction in Euclid's Elements. That says something to the effect of that the tangent lines must be equal if you draw lines out from where they're tangent to where they meet. Page 123. First mention of tangent. Oh. Book 6. Oh, man. Yeah. I'm looking for circles here, guys. I don't suppose he knows what a kite is. Nope. To touch. Page 51. I mean, like, he absolutely must have done this at some point. Circles are said to touch one another if, when meeting one another, do not cut one another. Okay, easy enough. So it actually does seem like it should be in that book. One may hope. Two circles touch one another externally. The straight line joining their centers will pass through the point of contact. Haha. Yes. So we know that one. C. Tangent C exists by Euclid Proposition, or Book 3. Proposition 12. Yeah. a circle, equal straight lines are equally distant from the center. Oh, okay. Yeah. And those which are equally distant from the center are equal to one another. So any chords that you want to draw that are of the same length must be the same as each other and must be in the same sorts of locations. So therefore the arcs are going to be the same, all sorts of other stuff like that. We want something with two different tangents. If a straight line touches a circle and a straight line be joined from the center to the point of contact, it will be perpendicular. Helpful. Equal circles make equal circumferences. Easy enough. Oh, there we go. Proposition 37 in Book 3 says, if a point be taken outside the circle, and from that point there fall on the circle two straight lines, if one of them cut the circle, the other fall on it. Oh, nope. Hang on. So this is talking about a point which can make a tangent and also draws a line through them, through like some random points in the circle. So that is not what we want. Let's see. FED is a right triangle because it has a tangent. We know that much. DB and DE are the same. We want DB to be the same as DE. That is not the point of this proof. Curses. Alright, book 4. Wow. About a given circle, circumscribe a triangle equiangular to a given triangle. Jeez. I mean, the people who are doing Euclidia definitely could do literally every single proposition all the way through the entire book. Somehow, I don't think they're going to. Book 5 is all about lines, really. It might be copying lines. Ratios. Yep. Book 6 is all about triangles. Other stuff. 7 line lengths. Must be earlier. Okay. Parallel postulates. Hey, Pythagorean theorem. Book 1, proposition 47. I didn't even need to read it. I just saw the diagram here. I was like, that's the Pythagorean theorem. Alright, book 2. Squares, rectangles, triangles. All sorts of good stuff, just not what we want. If on the circumference of a circle 2 points be taken at random, the straight line adjoining these points will fall within the circle entirely. I mean... I see. Yep, he went with the reductio ad absurdum on that one. And then we're back to book 3. Yeah. We might have to go through Euclid's Elements and literally do every single one of these just to have a bit of fun with it.
Mr. Q Casino, that's just part of the game. Want to always win? Play a vending machine.
Oh, I have to be able to do that, right? Set a goal.
Mr. Q, the casino you love to hate. And you'll love 100 free spins on Big Bass Splash with your first deposit. Play at mrq.com or on the app. UK 18+ residents only. Minimum £10 first deposit. 10p per spin. Free spin.
No, that's not... No.
All winnings paid in cash. Fees apply. Play safely.
Can we just cancel that? Because I don't know what I just did. Boo. Oh, I see. We're going to turn that off for now. Because I don't know what to do with it. There's got to be a community. Nope. Ooh, viewer rewards. I think that one's it. Not that one. Nope. There's a thing somewhere. Oh, I need to change. Awkward. We'll do that later. It'll be alright. We'll work on that later. Okay, so ooh. There is parity between these two things. Because this is also going to be R. R. So at this point, the only thing that we actually need is either confirmation that the angle is the same. Oh, wait, hang on. Wait. No, never mind. Right, it's still side-side angle. That doesn't help. Okay, I do think that here we could say that the distance to either of the tangents is going to be equal. Or something. Yeah, I think we have to be able to say that from any point, the distance along that tangent must be equal on either side. I don't have a number. I don't have Euclid's postulates or anything like that, but I feel like he would have said that somewhere. FB produced is a diameter, and the straight line drawn at right angles to the diameter of the circle from its extremity touches the circle. We know that. Okay, let's look up. Tangent lines to a circle are equal.
You love listening to your favorite artists, and we love listening to you.
Oh, gross.
So let's talk. To take part in our short survey, and you could win a month of gloriously
Intersection points T1 and T2 on circle C, and the new circle are the tangent points for lines passing through P. The line segments OT1, OT2. Here. Just in case anyone wants to follow along with my rambling. It is the Wikipedia page on tangent lines to circles, separated by underscores. OT1 and OT2 are the radii of circle C. Since both are inscribed in a semicircle, they are perpendicular to the line segments PT1 and PT2 respectively, but only a tangent line is perpendicular to the radial line. Thus, the two lines from P passing through T1 and T2 are tangent to circle C. We knew that. Draw any three lines that you want through the circle and then like interconnect every single one of them. Entrance points to exit points. All of them. Actually, that's not true. Okay. Found intersection points between the entrance points and two of the exit points. Its own A to A, A1 to A2. And also the one next to it, C2. Yeah, okay. according to the time-old tradition of holding a piece of paper up to the screen. Right. Those all make... Those all make intersection points that, when you extend, those intersection points align through those intersection points out to the edges of the circle. That gets us the tangent points. That's cool. How do you know that? Do the following with analytic geometry. Fine. Tangential polygons. Okay, cool. So this is one of those things where it's obvious that this is true, but we can't just say that it's obvious and move on. We have to actually find a better reason that we are allowed to mark this one equal to that one. Yes, again, there are tangents going out to the edge of the circle, but right now that's getting us a side angle side type thing, and again, side angle side, or sorry, side side angle. Angle side side. And it doesn't prove anything. If anybody wants to kick in here, feel free. Right.
Winning! Losing. At Mr. Q Casino, that's just part of the game. Want to always win? Play a vending machine. You win, you love Q. You lose, you hate Q. Mr. Q, the casino you love to hate. And you'll love 100 free spins on Big Bass Splash with your first deposit. Play at MrQ.com or on the app. UK 18 £10 first deposit. 10 plus free spins must be used within 48 hours of deposit. All winnings paid.
The side they share. The side that is the radius.
Hi Newman, you can listen to SE9 Part 1, including Family Matters, Hairdresser, and my new single, FU and UF, on Spotify now.
Side they share the radii and the right angles. Technically the only things we have at the moment. Hmm. Okay. Rather than going to ad break, right? It is 1 in the morning, so let's go find some friends. Let's go see our friend Buana, who is currently working on Fallout 76, and then maybe Dukov, Escape from Dukov, and various other cool things. So, I will see you all on maybe tomorrow, but probably Sunday. Well, no, okay. I'm doing D&D, so probably not Sunday. I'll see you all on Monday. We'll do some more, what's that? Math papers. So we'll go through the archive and see what I've pulled up and see what is math education and what is more like math history, and we'll see how things go. So if anybody has any questions on like how to teach math and things like that, feel free to come on in. If you have any questions that's like, I don't know how to learn math, please feel free. Ask anytime you want. Even when I'm gaming, I'm perfectly happy to stop and ask or answer all sorts of questions. I typically do things in terms of like needing to answer your real question, so give you a long-term answer. Although some people find that rather off-putting and like, nah, I just need to solve this one question. But things happen. All right, I'll see you all later. My name's Obi-Wan Pez. This is N Simplex Pachinko. Catch you next time.